Okay, so hello everyone. My name's Alexander Bell. I have worked with Integral Concepts Incorporated to provide support in educational material and consulting for data science and machine learning. This is the second webinar I'm doing with Ascendo Reliability. The first webinar I did in March was on supervised machine learning. I'm going to recap that briefly in this webinar. But in this webinar, I want to talk about the predominant unsupervised learning method, which is cluster analysis, and give some idea of its applications in various problems, including failure mode investigation. Hmm. So to begin with, just a quick recap. So on the 10th of March, I presented this webinar. So this is the summary slide that I provided at the beginning and end of that webinar. The idea here was that we had data from a large set of automobiles, so cars, and specifically we were interested in their engines, where for every single car we knew whether or not the engine was going to be okay in the near future from when that data was recorded, or if it was at risk of imminent engine failure. And in that webinar, I demonstrated training an artificial intelligence model and specifically a decision tree. So that's what's represented in the middle block here, which would take data from cars and would make a prediction as to whether or not it was okay or whether it was at risk of imminent failure. In addition to that, I showed that when we look at the model and we look at why it's making a decision between okay and failure, we can then understand and perhaps identify the different reasons for failure. And thus, this is one way we can investigate failure modes. Um, I'm going to recap in this webinar the terms like supervision and some basic things like AI and machine learning. What I want to say now is that this was supervised because we knew ahead of time for the data that we had whether the cars were going to be okay or fail. And we used that knowledge in order to make this predictive model. This is one form of machine learning. This is one thing that we can do with machines and with intelligent reasoning. But there's other things that we can do, which includes pattern recognition and determining separations and distinct groups of points in data. And so that's really going to be the focus of this webinar, which is cluster analysis. So I'm going to have a little representation similar to what I showed on the previous slide for this. Imagine if you have a set of data where there happens to be different kinds of points within that data, like different species of object, let's say. I'm representing this as circles and triangles here, but imagine from the perspective of the machine, these are all just data points. So it doesn't really know if there's any difference, and we may not know if we just look at a massive table of data if there are any distinct groups. The idea of cluster analysis is to look at the distance between points, points that are very close together, and also points that are very far apart. And using the distance here, be able to identify if there are significantly distinct groups that are well separated and are kind of clumped up in clusters. So the general flow of cluster analysis I'm showing here is that you have raw input data. It's analyzed by an algorithm, and I'm going to cover a couple of clustering algorithms in this webinar. And then it tells us how many clusters it finds or tells us what points are assigned to which cluster. And we'll provide a summary of those clusters. Okay, so I'm going to go into much more detail about cluster analysis in the middle of this presentation. As with my previous webinar, I'm going to present this in three parts. The first part, I'm going to just talk a bit about AI and machine learning. And for anyone who was in my previous webinar, this will be a recap. And for anyone new, this will be just introducing and being clear on the terms that we use in machine learning. In the center of the webinar, I'll then talk about cluster analysis, and then at the end, I'll talk about applications. Specifically, when I recap machine learning, previously I was talking about supervised analysis, and I gave the kind of analogy for how human beings reason, specifically with object recognition, where you know what an object is. In this webinar, I'm going to include unknown pattern recognition in this demonstration. I'm then going to talk again about artificial intelligence and machine learning and how they are related to one another. And finally, I'm going to recap supervision because, as mentioned previously, I talked about supervised analysis. In this one, I'm going to show unsupervised analysis for comparison. In cluster analysis, I'm going to be talking about definition. So what is a cluster exactly? what is the centroid of a cluster, which is often computed to represent it, as well as the difference between partitioning data versus clustering data. I'll talk about quality and how we assess the quality of a cluster analysis and its outcome, and also the notion of cluster tendency. So before we even do any analysis, we have statistics that we can use to check whether or not a data set in general is likely to contain any clusters. And then I'm going to cover a couple of algorithms, some very basic algorithms in clustering. The first is k-means, and the second will be hierarchical clustering. Then in applications, I'm going to be using Minitab, so toward the end of this talk, which implements both k-means and hierarchical clustering. I'm going to illustrate both using that automobile failure dataset, which I'm going to recap the basic features of when we get to it. And I'm going to show how it can be used, both these algorithms can be used for failure mode investigation. I'm also going to use a new data set. This is a real data set from a machine learning repository, the purpose of which was to target and predict miles per gallon, so fuel efficiency in automobiles. I'm going to use that to illustrate feature assessment with cluster analysis, so that in addition to clustering points of data, you can also cluster variables, the columns of your data set, and group them based on similarity and difference. And that I'll explain as I go through cluster analysis and when we see it in applications. Okay, so for the first part of the talk, I'm just going to recap a lot of stuff, just the background of machine learning and AI. So a simple definition of artificial intelligence is the study of in computer science. So it's a subset of computer science where we're using computers to mimic what we as human beings do with our brains when we're using our intelligence and we're reasoning about things. There's various ways that we use our intelligence. What I illustrated in my previous webinar was object recognition or classification. So here we have someone who's already seen a bird before, but has already maybe seen other things and knows what they are. You take input, in this case, some visual stimulus, which is then transmitted to your brain. There's some processing going on, and then you recognize what the object is. Okay. So this is an example of known object recognition. So you can get a set of if you have a set of objects which you're told what they are, this is a bird, this is a bird, this is a bird, but then you have lots of different objects for comparison, your brain learns to take in features of the object you're looking at, compare it with what you've learned, which is a concept, and then output or make a decision or simply recognize what it is. So AI is taking an activity like that and getting a computer to do it. So a computer can take in information, it transmits it to some processing unit, learning and or classification takes place, and it's able to recognize what that object is. So this in a nutshell is AI, which is again a subdomain of computer science. Now, what I didn't show in the previous webinar is a different kind of activity, which is unknown pattern recognition. So this is using our reasoning just to identify groups in data where we don't necessarily know what the objects we're looking at really represent. Okay. So I want you to imagine, say you don't know what a cylinder or a cube or let's say a banana is. You just see this collection of points or collection of objects. Is there anything intelligent that we can do with this? Well, taking in this data, we can look for patterns, we can look for associations, we can look at what is similar to another in this collection of data and what is dissimilar, so what's very different. And then doing this kind of intelligent reasoning, we can say, okay, you may not know what each of these things are, but you can see that there are 3 different kinds of object in this collection. You can see that there are 5 of this object, the cylindrical one, and then 4 of each of the other. So this is a representation of the root of clustering. This is what clustering is about. It's about taking a mix of data and, if it makes sense, being able to distinguish and find distinct groupings within that data based on similarity and dissimilarity. Okay, machine learning then, how does that relate to AI? So as I mentioned, AI is a branch of computer science. When it comes to mimicking intelligent reasoning with machines, you don't need to use data to do it necessarily. A programmer can write a program like a flowchart to take input, follow a predefined series of steps, and give output, and have the computer doing something that mimics intelligent action, making decisions. Okay. What defines machine learning separate from AI is that it is really based on data. So I bolded the word here. We're using a data set itself to then train the computer to come up with an algorithm. Well, following an algorithm, we give it to come up with a model that can then make predictions or provide outputs such as cluster identification. Okay, so that's machine learning as it relates to AI. There's a lot of different ideas and methods that exist in machine learning. The bottom left, I'm representing a decision tree here, which I presented in my last webinar. I'm also representing simple regression because again, you have the true values for a set of data, and you create a model from that, from which you can predict values for new data. I'm showing what's called k-nearest neighbors here in the middle top. In the top right, this is clustering that I'm representing, and this is what I'm going to talk about and what I'm talking about in this webinar. I will mention, given its popularity, that deep learning is a subset of machine learning. So it does these classification regression tasks using an object called a neural network. And this is the basis of a lot of popular algorithms like ChatGPT or Gemini or other large language models that we're using today. So just for interest, I wanted to just show you and situate that relative to machine learning and AI. But for this talk, again, it's this little bit in the top right here that we're going to focus on. The final slide I have then for machine learning is I'm just going to recap supervision and unsupervised problems. So there's two fundamental divisions of problem and correspondingly two different kinds of algorithms we think of in machine learning. A supervised algorithm is one where we know the outcomes for a sample of data, and then we're using that truth to create the model. This is further subdivided into two kinds of supervised learning, which is classification and regression, based solely on what is the target, what is the thing we're trying to predict. Okay, if the target is a class, like a categorical variable, for example, logistic regression, we call this classification. If the target's a number, for example, as you're doing standard linear regression, then this is a regression algorithm in machine learning. But in this webinar, I'm going to talk about this whole other class of algorithms and give the prominent example of that, which is clustering, and this is unsupervised learning. Here, there is no target or truth. We're not trying to predict a particular variable or look at the association of one variable, especially with others. Here, we're just looking for patterns and associations between the variable, and as indicated on the previous slides, we want to know if any, there exists some distinct patterns or groups within the data. And then we want to be able to summarize and understand what do those groups represent. Okay, so I've covered an introduction to machine learning. I'm going to move on now to discuss cluster analysis, the basic theory and algorithms. But I want to ask, does anybody at this point have any questions about the material I just covered regarding AI and machine learning? Okay, so I'm not seeing or hearing anything, so I'm going to just continue on and discuss cluster analysis. Okay, first question and definition I want to cover is what exactly is a cluster? So we have obviously a good intuitive sense of it being a group or a clump of points. A more precise definition that's useful for creating algorithms is that a cluster is a group of data points where they are similar to each other. So in a line, I'm going to expand on this a bit with membership, but in a line, that's the idea of a cluster. I'm also going to go on in the next slide to discuss the analogy between similarity and distance, geometric distance. So in a nutshell, similarity is like closeness geometrically. Furthermore, we have that if we have a point that is a member of a particular cluster, what it means is that that point is more similar to the other points that are in that cluster than it is to other points that are not in that cluster. Okay. Again, we're going to look at what this means with respect to distance. But first of all, just from this basic idea of similarity and dissimilarity, imagine we have a set of bolts and washers, and this is our data set. What would it mean to cluster that data? Well, clustering would be to identify that the bolts are similar and very dissimilar to the washers, and the washers are similar to each other and dissimilar to the bolts. So there are two clusters here, both contain four objects, a cluster of bolts and a cluster of washers, okay? And that's just based on similarity. So that's what clustering would mean if we were just looking at a set of objects like this. So as mentioned, similarity is analogous to distance mathematically. So in general, we consider points to be very similar if they're very close geometrically together in the data space. So if we consider a two-dimensional set of data here, this could be two numerical variables, and we scatter plot some points. And I'm going to create a number for simplicity, very idealized clusters here. If points are very close together, the distances between them are very small, then we consider them to be very similar. If distances between points are very large, then that's analogous to being dissimilar. They're very different if they're far away from each other in the data space. Now, this applies whether we're looking at two-dimensional data or we're looking at 10-dimensional data where we can't visualize it anymore, but we have metrics that will still measure distance, and then we can still apply that definition of clustering. Okay. The centroid, if you've not heard it before, sounds kind of fancy, but it's very simple. It's just the average of a set of members of a cluster. It's a very easy way, like when you compute the average of a set of data, it's a simple one-number summary, which you can use then to kind of summarize and understand what that cluster is. So it's a way of simply representing the cluster. So if we have a set of points here, the centroid of that cluster is just the mean point. In two dimensions, here it's just x bar, y bar, and that's the centroid. So as mentioned, it can be used to summarize the cluster and to compare clusters. And it's one thing we can use to kind of understand what the cluster might represent, especially when we look at it in relation to other clusters. And I'll illustrate that when we come to the examples in this talk. So now I want to talk about the term partition and cluster. So a partition, and specifically a hard partition here, is an assignment of every data point in the data set you're analyzing to a distinct group. Okay. I'm going to show why this is different to cluster in a sec. So suppose we have points like this where you can suspect maybe there's two clusters here. Again, that's based on that definition of similarity and dissimilarity. What is a partition of this data? Well, the following is a completely valid partition. We can say that this point, and then this point over here, I hope you can see my cursor, is one partition. And then these 2 points and these two are a second partition, and then just these three here is a third partition. So we've split that data into 3 groups, okay? Whether or not a partition of data, which is splitting it into groups, distinctly, really identifies clusters, that's an entirely different matter. Okay, it's very important to be aware of this concept and this difference, because clustering algorithms always are going to produce partitions. So when we look at k-means and hierarchical clustering, the end result is that every single row of the data set is going to be given an ID. It's going to be given an integer that tells you which group that point belongs to. That's not necessarily a cluster, that's a partition. Whether or not, again, it really satisfies that definition of similarity and dissimilarity is a different matter. This naturally then leads us on to the idea of quality in clustering. Okay, so if we have a partition of data, we've got this group assignment. How do we know if it really does represent clustering in terms of similarity? Okay, so we can apply tests to groups to then check how well that result meets that definition, and this is the quality of clustering. There's a lot of different metrics. For the sake of simplicity in this talk, I'm only going to discuss one, and that is the comparison of the scatter metric that compares within cluster to between cluster scatter as a ratio. Okay. The within cluster scatter is just the sum of the distances of all pairs of points that are in the same cluster. The between cluster scatter is the sum of distances of all pairs of points that are not in the same cluster, i.e. they're between different clusters. Now, if you think about the definition, it's fairly straightforward. Then we expect that this top number should be small, and this bottom number should be larger than the top number. And so we would expect this to be less than 1 in value, and the smaller it is, the higher the quality of the clustering. So if this is close to 1, that suggests a problem with the quality. But as mentioned, there are a lot of different metrics that can be used with various strengths and weaknesses when it comes to testing the quality of clustering. I think the final concept I want to cover before I then go on to algorithms is the notion of cluster tendency. Okay, because just because we have a data set doesn't mean there are any clusters. A lot of data sets have no clusters. They're just a kind of cloud of points. Okay. There are tests we can apply to see if there are likely to be clusters. For the sake of brevity, I'm not going to go into this mathematical details in this talk here, but I'm going to share with you one statistic, which is called the Hopkins statistic, and just give you an idea of how it works. So if we use H to represent this statistic, if H is about 0 or very low, this corresponds to a uniformly spaced grid of points like this. So obviously there's no real clustering evident in a data set which has a very low Hopkins statistic. If Hopkins statistic is around 0.5, then this corresponds to randomly placed points. The one on the left isn't random, of course, it's incredibly organized and structured. If you take randomly spread data, it might look like this, where there's variation in density in the space, but still there's no real indication of separation or clustering. If the Hopkins statistic is close to 1, however, that's an indication of points that are heterogeneous and well separated in the space. And this is represented by a H of approximately 1, or getting closer to 1. So this is one basic test you can apply to a data set before you do any kind of analysis, just to see, does it make sense to look for clusters in this data? Okay, so now I've just covered some of the basic theory and ideas of clustering. I'm going to move to talk about a couple of algorithms. To kind of motivate this, I'm going to ask the question, can we just check the cluster quality for all possible partitions? Imagine you have your set of data points. Well, there's a finite number of ways you can assign them to different groups, right? And we know we can check the quality by looking at the within and between scatter, amongst other things. So let's just make a list of all those groups and then test all of them. Now, I'm not going to explain the maths of this. I'm honestly just including this because I think it's funny how many Ks there are in this formula. But the simple point of this is this is showing you if you have n rows of data, that's instances. In machine learning, we use the word instances typically to refer to rows, items of data. And you suppose you want to sort them into K clusters, and this tells you how many different ways you can do that. The main point I want to make here is this gets incredibly large, even if you have a fairly small data set. And it means that the idea of doing this brute force, let's just make all the partitions and check them all, is not tractable. It's not something that you can really compute in a reasonable amount of time, even on a very large, expensive, powerful computer. So in practice, we need more efficient methods. So one of the most popular and basic methods in clustering is called k-means. It's a stochastic algorithm. What that means is it involves an element of randomness. Oftentimes in computer science, randomness helps us to, we sacrifice absolute precision, but then we gain a lot in terms of computational speed and efficiency. And you'll see what the randomness is in a sec. It's pretty simple. For this and the other algorithm, so an algorithm is just a logical series of steps, and I'm just going to walk through the steps of this. The first thing to do is that you specify ahead of time the number of clusters that you're searching for. So k-means is an algorithm that requires you to specify the number of clusters. There are other clustering algorithms where you don't do this when you're interested in knowing what number of clusters is. But for k-means, you specify this. When it comes to wanting, for example, let's suppose you don't know how many clusters there are, you can just try a few different things and then check the quality with k-means. That's one way that k-means can also be used to search for the number of clusters. But as it is, the algorithm requires you to specify how many clusters to begin with. The second step is to randomize initial points. So for example, if k was equal to 2, you would randomly pick 2 points to begin with in the data space. And then these points, so you initialize these points in the data space for however many there are, and those are the cluster centers. Then every row, so every point of data that you have is then assigned to the nearest cluster center, okay? Then in step 4, we update every center to be the centroid. So we take the averages of those collections and we kind of shift those centers to be the averages for the instances assigned to it. So I'm going to talk a bit about my machine learning methods course towards the end of this, where I have some animations illustrating this. But since I'm covering hierarchical clustering, I'm not going to go through the animation here. I'm just going to kind of give you an idea of what happens, is that steps 3 and 4 are going to be repeated until there's no change in cluster membership. So what essentially happens is you initiate these central points, and then they will shift and shift and shift as you repeatedly assign membership until eventually there's no change in membership. So they kind of settle down. And once those points have settled down, that's your answer. That gives you your resulting assignment, your hard partition. So this is one way of very quickly, it's very computationally fast, finding a set number of clusters for a data set. The other kind of algorithm I want to discuss, which is also very popular, amongst other areas, it's used widely in genetic analysis, but also just for a lot of methods, is hierarchical clustering. And a particular kind of hierarchical is agglomerative, which means bottom up essentially. You can also do divisive hierarchical clustering, which is top down. But in this webinar, I'm just going to talk about the bottom up approach. And I do have a visualization on the next slide, which is going to illustrate this. But if you have n points of data, the first step is to assign each data point to be its own cluster. So you just start off with a lot of clusters. Every point is just its own cluster. Then you find the closest pair of points in space and you merge them into a single cluster. And the first time you do this, obviously, you will then obtain a cluster that has 2 points in it. You then just repeat this step until there's only one cluster that contains all of your data. And that, in a nutshell, is hierarchical agglomerative clustering. Okay. There's a couple of things that I'll just mention here. I'm not going to go into too much detail in this talk, but obviously, one key aspect of this, and for a lot of algorithms in general, is how do you measure the distance between clusters? The distance between points is fairly straightforward. You can use, for example, a Euclidean distance. But to measure between clusters, there's various ways you can do this. For example, one way is you can measure the distance between the centroids, and that's just resolving to measuring the distance between points. The way we do this is calling a linkage function. So it just means there's various ways you can measure distance between clusters. And one thing I'll mention here, and I mentioned it earlier in the talk, is that I've been talking about clustering applying to data points and rows of data, but we can also apply it to columns, and we're going to see it applied to columns in a sec and during the applications. So I think the final thing I'm going to do before I'm going to pause again for questions and then move on to applications is just illustrate what hierarchical clustering looks like in a very simple case. I've artificially created this this state on the left here where there are 2 clusters just by visual inspection. There's 5 points, A, B, C, D, E. To begin with, on the right, I'm showing what's going to be the construction of a dendrogram, and I'll explain what that is, which shows how clusters are formed as we run this algorithm. So everything starts in its own cluster. I've got a distance of 0 here, which equivalently means like a point is the greatest amount of similarity you can have is a distance of 0. If we consider some small distance, epsilon1, we'll get these 2 points joining together. So this is the smallest distance at which 2 points will be merged into one cluster. And then at this step, we will have 4 clusters. And then if you look at this, you can probably see that D and E are the next closest 2 clusters at this point. And so they're going to be merged at some distance, epsilon2, which is a bit larger than the first distance. At this point, we have 3 clusters. These 2 points are in one cluster, A and B are in one cluster, and C is all by itself. But you can see that C is fairly close to this cluster, certainly much closer than these guys are. So C is going to be the next point that then interacts with that A and B, and they're going to be merged into one cluster of 3 points. Now at this point, we've captured the 2 clusters I intended it to capture by setting this up. But the algorithm's going to keep going until everything's merged into one cluster. So after some larger distance, epsilon4, everything's going to be merged into one cluster. And so this is, you can see, a bottom-up approach to merging points and forming clusters. Now, a key idea here is persistence. Okay. You can see that for a range of distance, nothing changed. So usually when we do hierarchical clustering, you'll see that at small distances, there's an awful lot of activity. Points are all being merged into lots of little clusters. But when you see gaps where nothing is changing, when you see a visualization of hierarchical clustering, that's indicative of the presence of a number of clusters. And at this point, this would indicate 2 clusters, because 2 clusters remain the same over a long range of distance. So the final thing I'm going to cover with respect to hierarchical clustering is the topic of the dendrogram. So a dendrogram is commonly used to show the outcome of hierarchical clustering. It really kind of shows you a visualization similar to the example I just ran through. I'll mention that the prefix dendro here is from the word dendron, which is Greek for tree. So it's like a tree diagram. Um, the uh, the data I'm illustrating here is from the IRIS dataset. So this is a very popular dataset in machine learning. They're measurements from flowers for different species of flower, and it's a classification data set where you want to try and tell the difference between these flowers just based on this measurement. But here, what I'm illustrating is taking features, so these are actually columns, and seeing how similar they are and doing a hierarchical clustering based on feature similarity. So we can see, for example, that petal length and petal width of flowers are very similar. The actual metric is correlation, so it means they're highly correlated variables. They merge very quickly into one cluster. Sepal length and sepals are kind of like petals that grow from a stem, I believe. They're not very far away. But the width of the sepals is quite different. So we can get an idea looking at this quickly that the sepal width is very different to the rest of these measurements, and that for a long range of distance, we have two clusters here. We have these three flower measurements forming one cluster and one that's separate. Okay, so that concludes the section just explaining what cluster analysis is and a couple of algorithms that I'm going to illustrate. Again, I'm just going to pause for a second here just to see if anyone's got any questions they want to ask about the material I just covered. Okay, I'm going to move on now to discuss applications. So in my previous webinar, I introduced this data set. I'm just going to recap it here. So this is the engine failure data. This is artificial. So this is data that I generated to illustrate binary classification. So we had two different kinds of automobiles whose engines were going to be okay or whose engines were going to fail shortly after when this data was collected. And we had 8 input variables. And yes, I believe they're all continuous variables. They're listed from columns 2 to 9 here. So they included temperature, oil level, rotations per minute, tire pressure, sound, maximum average speed, and airflow in the engine in gallons per second. And so the classification task was knowing the truth, because we know whether or not the engines were going to fail in this case, predicting based on this data whether the engine was going to fail. Okay, so that was a supervised binary classification problem. Now, I want to imagine that we only had the rejected cases, the cases of engines that had failed, rather. So there's 127 of these, okay? And there's no outcome target variable. So we don't know for these cases whether they were okay. Well, we know they failed because I selected them as such, but if you collected this data, you just know these are failed engines. And we're not trying to predict failure in this case, okay? So we just have a set of 8 variables. Now, in this case, we can certainly investigate failure modes, and we can use one method we have to do that is unsupervised machine learning and cluster analysis, which I just covered. In general, again, cluster analysis is trying to look for different distinct types and well-separated types of data, whatever that data is. Well, in this case, what we're looking at is failed engines. So that translates to different types of failed engine, i.e., this corresponds to investigating for distinct failure modes, so reasons why engines might have failed. Okay, so for simplicity of the illustration in this talk, I'm just going to take a two-dimensional case, a scatter plot, and also knowing that oil and airflow are major factors that contributed to engine failure. You can see clearly that there are two clusters in this data just from visual inspection. They're not kind of nice and spherical like I was illustrating the examples, but they are very well separated. So you have a sparse cluster here, and then you have a narrow cluster here. I'm not going to go ahead and do an interpretation of what they represent just yet. You could probably tell at a glance. But I'm going to show how cluster analysis in Minitab can be used and then interpreted for this data. So in Minitab, if you look under statistics and multivariate statistics, you'll see that Minitab has a number of clustering algorithms. Specifically, they have k-means and hierarchical clustering. And the hierarchical clustering is provided both for clustering rows of data, which is observations, sorry, and columns of data or variables. And you can see the little orange dendrogram here. So that's what I was presenting previously, which is what you would use to interpret hierarchical clustering. For now, I'm just going to use k-means on this fairly simple example. I'm going to specify the number of clusters. As mentioned, that's a required input for using k-means. So that's going to dictate the number of initial random points that are created. I'm also going to go into the storage function for this GUI, and I'm going to ask it to put the membership, which is the essential output from clustering, into an additional column. Once I've done that, then using two cluster centers, I obtain the following output. So in column 10, after all of the engine variables or the automobile variables, I have the ID is just a couple of an integer, which is 1 or 2. So that identifies which cluster the algorithm assigned these points to. I can then scatter plot this data with groups using the cluster ID, and then I can check visually that it did indeed identify and capture those two clusters as I see here. Now, in this case, it happened to do it successfully, mainly because they're very well separated. One thing I should mention is that k-means does have some limitations. One of them is that it really assumes spherical or round clusters when we're looking here. If these groups were a bit closer together, we might not see such a clean separation, and then we'd want to use a different algorithm, like hierarchical, with an appropriate linkage function to be able to deal with this. Because one of these clusters is kind of like a long smeared strand of a cluster, which isn't very spherical at all. K-means happens to work here because they're well separated enough. I'm also going to use this to illustrate the quantitative output you get from clustering. So as you recall, clustering gives us partitions. We know that they're clusters here by the definition because we can see it visually. But in general, you'll get a partition, and if it's higher dimensional data you can't see so easily, then you need some kind of quality test. We see that there's two clusters, one with 56 members and another with 71 members. We get some readouts of variance within these clusters, how spread out those points are. So there's three different ways we can see one is more compact than another, and that's really the red cluster here is more kind of squished and compact. These points are very close. The blue cluster is more sparse. And we also get the cluster centroids here, which are just the mean points. And again, this is a good way to summarize. So if we look at this, we have two clusters. One cluster has a pretty good oil level, but has a relatively low airflow to the engine. And then the other cluster has good airflow. It's got an average of over 15 gallons per second, but the oil level's pretty low. It's below 6%. So this is what commonly happens then, because I did this a lot in my medical research, and cluster analysis is widely applied in medical research to subtype disease, for example. Like we want to explore the different kinds of disease that exist. Once you've done an analysis, you then produce a kind of a table and try to explain, well, what do these clusters actually represent? So if you think back to what this problem's really about, we're looking at failed engines. And so these are different kinds of failed engines. And so what we're seeing here is failure for different reasons. Cluster 1 appeared to fail because the airflow had dropped below what was required to properly cool the engine. So this is failure due to low airflow. Cluster 2 has a very low level of oil with sufficient airflow. And so we could summarize then that cluster 2 is failure due to a lack of oil within the engine. Okay. And so that's the endpoint for cluster analysis is cluster summaries. I'm also going to demonstrate just using hierarchical clustering on rows in the same data for simplicity. So we select from statistics, multivariate, and we can cluster observations. It's important observations, not variables. The variables are columns, which I'll illustrate after this. If we cluster the observations, then when it comes to the inputs, Minitab does want you to put a number of clusters. This isn't important for it's not going to make any difference to running the algorithm. It's only going to affect the output. I know ahead of time that I want to see two clusters, so I'm going to put two here, but I will illustrate when I look at the next problem. I'm just going to throw the number 1 in because the thing that I really want to look at here is the dendrogram. The dendrogram is what's going to tell me how many clusters are likely to exist in the data and if there are kind of varying levels of clustering. Okay, there are a couple of objects, for example, the linkage method, the distance between clusters, I'm going to use their centroids, and I'm just going to use the standard Euclidean distance, which is the standard distance as you would see in geometry between points. So the dendrogram for this data looks like this. So as you can expect, because there is over 100 points here, it's much busier than when I showed the illustration with variables. You can see that there's one cluster where lots of activities happening at a small scale. There's loads of points really close together that are getting merged. And then there's another cluster here which takes a bit longer to merge into one cluster before we see, again, there's a long range at which nothing's changing. I'll also mention that when I was illustrating clustering, I was starting from a distance of 0 and I was talking about increasing distance. This scale here in similarity is precisely analogous. 100% similarity is the same as 0 distance between points, and then similarity drops off as the distance increases. Okay, so you can also just think of this as distance. Um, so it happens that the color came out identical here, which is helpful. You can associate this with the scatter plot of airflow and oil level, and see that the red points, this kind of long smeared cluster here, that's this part of the dendrogram, and then you would cut around here and see this cluster. So because I selected two clusters ahead of time, you could output the cluster ID association from this dendrogram, and it would give you exactly the same picture as when we used k-means. Um, but generally speaking, when you're exploring with hierarchical clustering, it doesn't really matter how many clusters you specify in the algorithm. You really just want to see this dendrogram and then read off the likely number of clusters from there. Okay, I'm now going to move on to one more demonstration. I'm going to use a real data set, the AutoMPG data set for this, and just show how we can cluster variables using hierarchical clustering. So this data set comes from 1993. It was actually used to introduce a decision tree algorithm by Quinlan, who's a famous data scientist who's developed a lot of decision tree theory and algorithms. So I think I've got an illustration of the features of the data set. I'll say that I downloaded this. These are all freely available from the UC Irvine Machine Learning repository. The Iris data set, which I kind of illustrated earlier, those flower features, is available there as well. So these are well-known data sets in machine learning. In this data set, the task is to predict miles per gallon. But what I'm going to do is I'm just going to use this to illustrate looking at how the various continuous features here are related. So I'll go to stat, multivariate, and now I'm going to look at clustering variables. Okay. Minitab summarize this as reducing the number of variables, and you can use this for what we call dimensionality reduction, reducing the number of columns in the data. But I'm going to use it as a tool to very quickly look at associations between the variables in the data. I'm going to use all the continuous features. So I am going to include miles per gallon, which is originally the target feature, but I'm just thinking of it as another feature here, as well as displacement, which is proportional to the size of the engine in the car, horsepower, weight, and acceleration. And I'd also mention that these cars are from around, I think, the 1970s and 80s. So this is relatively old data now. When it comes to the distance metric, I'm not going to use Euclidean distance. When I want to know if two variables are similar or dissimilar, I'm going to use correlation. And I'm going to use the notion that if variables are highly correlated, they're similar and they're close together. And I'm also going to use absolute correlation in particular because I don't care about it being positive or negative correlation. I just want to see high correlation, meaning that they're very similar. Low correlation is they're dissimilar. And as mentioned, I'm just going to pop the number of clusters to be equal to 1 because I'm not really looking for clusters at the beginning here. I just want to see the dendrogram. And then if I do want to cluster these variables for any reason, I can reset this in order to get my desired output. So the dendrogram for this data looks a lot simpler. That's generally the case. You usually have fewer variables than you have rows. In genetic data is the extreme opposite, and you will see if you ever see genetic data, we call it omics data analysis, like transcriptomics and genomics. There's often a lot more variables than there are rows, and these kind of representations are used widely there to group genes. But here we're looking at these automobile features. One thing that should stand out immediately is that acceleration as a feature is quite far away from everything else. I'm going to illustrate on the next slide what this looks like in terms of correlation, which is how we're measuring these things. But at a glance, you can see that if you wanted to predict miles per gallon for a car, at least for these cars that were sampled quite a long time ago now, acceleration would probably be the least helpful thing that you'd want to look at. The most helpful things would be displacement, weight, or the horsepower of the car. And if we look at all of these variables, we see that displacement and weight are very similar. Again, the term displacement here, I believe, is referring to displacement in the engine compartment. It's really proportional to engine size, so it makes sense that there is a correlation between how big the engine in a car is and how heavy the car is, as I believe the engine is one of the heaviest components. And as you'll see, as you can expect, this is a pretty strong positive correlation. So if you remember, acceleration is different to everything else, and then displacement and weight are very similar. I think this is the final slide I have just to illustrate what this means in perhaps more familiar visualization to a lot of people here, which is just looking at a scatter plot and looking at the correlation coefficient. Weight and displacement were very close to each other in that dendrogram. They have a very strong positive correlation of greater than 0.9. Acceleration and weight, there's a mild correlation there, but it's much weaker. And it's minus 0.42. But again, I used absolute correlation. So the important thing here is the 0.42, which is significantly less than 0.93. Okay, so this is what the dendrogram is summarizing, but across a large number of variables. Okay, so I've reached the end of the webinar now. I'm going to summarize what I've been talking about in cluster analysis, and then I want to talk briefly about a machine learning methods course that I've been developing with Integral Concepts and Ascendo Reliability. But first, to summarize this, in this webinar, I talked about unsupervised machine learning and how we can use this to identify patterns and associations in data. Where there is no target variable or nothing that we're specifically trying to predict, we're wanting to see if there is any kind of distinct grouping or not within the data we're analyzing. Cluster analysis is one of the predominant forms of unsupervised learning, in which we're identifying distinct groupings within data. And this can apply either to rows of data or to columns of data. So we want to see if there's any distinct groupings based on similarity and distance or not. I covered a couple of clustering algorithms in this talk, which was k-means and hierarchical, but there are a lot of other algorithms. Actually, in my master's research, I used something called density-based clustering, which is really cool, and it's something I might mention when I'm talking about my course. And yeah, specifically, when we looked at applications, we were looking at clusters in data on failed units and seeing how that could represent failure modes. But just to give you an idea of maybe some other applications, if you have customer rejections, like if customers are rejecting products, a cluster analysis there could tell you for the different reasons why customers might be rejecting products. Or maybe you find there's no clusters and you would conclude that there's one primary reason, that there isn't like a difference that exists within the reasons they're rejecting. Okay, but there is a lot of different ways that cluster analysis can be applied to your problems. Okay, before I finish this talk, I want to talk a little bit about the machine learning methods course. So this is a comprehensive training course that I've developed on the foundations of machine learning methods. This is a course that I've recorded videos for. I have 20 plus hours of lessons on these topics. And I think, yes, there is a certificate. I see, Carl, you're asking about certificate of attendance. There will be a certificate available for taking these courses. So there's 20 hours of lessons and 10 hours of exercises and solutions where I will talk through and explain exercises and then go over solutions in detail. And there's exercises and solutions for every lesson. This was developed in and hosted by Ascendo Reliability. And here's an example of one of the videos that are embedded in the pages there. So I cover a wide range of predictive analytic algorithms. One of the main real focuses and reasons for this course is that they've become popular and they're implemented in statistical applications, including Minitab, as I've illustrated here. But in my previous webinar, I illustrated the supervised machine learning algorithms, including decision trees and Minitab. But I also know that reliability software like JUMP is also implementing decision trees and predictive analytics. I haven't got time to go through the whole thing here, and it's a lot, but there's 7 modules I've developed for this course over 44 lessons. As mentioned, every single lesson has exercises and solutions that I've handcrafted to them. I cover very basic concepts, so I've made the course to be very widely accessible to people. You don't have to have a strong background, I believe, in mathematics and statistics to get a lot out of the course. I kind of explain the key ideas from the ground up. I cover statistical methods, and then this block here on data pre-processing is useful not just for machine learning, but for any data analysis you do. It's very important to prepare, to clean, and as best you can provide high quality data, because it's quite common in practice that data has problems you have to handle, and if you don't handle them effectively, then it's going to really curtail anything that you get out of them. And then the final modules here, there's a module on cluster analysis because I wanted to cover unsupervised learning. I cover in more detail what I covered in this talk, but also density-based clustering I cover in the final lesson there. I go over regression modeling. A lot of that will be familiar to a lot of people from a machine learning perspective, but I also cover spline functions and regression splines, which are very powerful methods and probably new to a lot of people. And then the final modules, I cover decision tree theory and decision tree algorithms, as well as some ideas like gradient boosting, which is used in ChatGPT and a lot of the most powerful algorithms today. The course is live now and available for registration on Ascendo Reliability. So I'm sharing the link here, but I believe these slides will be available after this talk if you want the link. The standard price for the course at the moment is $11.99 for 6-month access to all of those course materials. But we are running a 25% off for the first 10 registrants before October 31st. If that's something you want to take advantage of when you're going through the course registration process, you just need to make sure you put MLM-first-10 into this coupon code box. Okay. To end with, I just want to make a couple of acknowledgements. So from Integral Concepts Incorporated, I'm very grateful to Elise Wax, who's the president and founder of the company, and her husband, Steve Wax, who's the principal statistician at Integral Concepts, for their funding and their support for me as I've been working with them and in part developing this course. And also to Fred Schenkelberg, who's helped me in putting together the videos and the learning materials for the course and all the effort that he's put into creating and hosting the course online on his site, Ascendo Reliability. So with that, thank you for attending my webinar. And yeah, I'll open the floor to any questions or comments. Are you there, Fred?
Yep, I'm here.
Yep.
No, when I was going through setting up the course, I paid a lot more attention to the cleaning up the data part. And most of them I knew have used, or this is a technique to get rid of, deal with missing data and stuff like that. But there were a couple others in there that I had never seen before, and so look out next data set.
You're welcome, guys. Yeah, I think do you want to clarify about the certificate of attendance?
Sure. Yeah, it's we do that with most of the courses, is that once you've completed the course and we trust that you got something out of it and then used it and watched it all and then just click through. There's each lesson has a button that says, "Oh, I'm done with this one. I've completed it." And once everything is completed, then the certificate will be available on the course page, I believe it is, or at the top of the page, that you can then open that up and print it or download it or whatever you want to do with it. And it's basically a certificate of attendance or of completion. And it's useful for, and it has, I think, this one, because it's through Integral Concepts, you guys have ability to offer CEUs. So it has, I think, 3.2 CEUs in it, if you're after that. And that's similar for anybody that needs to recertify for professional development. It does that. And the certificate usually is sufficient for most organizations to do that, to score those points. All right. Thanks, Nate. Handful of others. Thank you all for attending. We had a decent turnout today. Who knew people wanted to know this much about, advanced statistical techniques?
I do see a question about time series analysis.
Oh, yeah, yeah.
So I don't specifically talk about time series analysis, but I do know that a lot of methods are applicable to the time series. But a lot of what I talk about in the course is really its classification and regression. So predictive analytics is about based on a set of data, predicting a class like a label or predicting a numerical output. I think something like time series data would require some pre-processing to obtain features that you would then use for classification or regression.
All right. Looks like people are spearing off and gratefully enjoying the finishing a couple minutes early so they can get ready for their next meeting.